Now discuss the energy level diagram for molecular orbitals. These energy level diagrams are of great importance because we can calculate the magnetic nature, we can calculate the bond order, we can write the electronic configuration for the molecule using these diagrams. So let's understand first the meaning of the bond order. See, bond order tells us about the number of bonds which are present in a molecule. It is defined as half the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbitals, right? So let's start with the hydrogen molecule. See, the hydrogen molecule is having the hydrogen is made up of one electron. The atomic number of hydrogen is 1, so we write the electronic configuration as 1s1. So this is one hydrogen atom, this is another hydrogen atom, and the two atomic orbitals that join to form the molecular orbital. So as this is an s orbital, so we have the sigma orbitals. So this is sigma 1s. We can write the electronic configuration. So molecular orbital electronic configuration is sigma 1s2. The bond order can be calculated as half number of bonding electrons, that is 2, minus the number of anti-bonding. As there is no electron, so we'll write it 0. So the bond order is 1. So that shows that hydrogen has one bond, right? Now we come to the hydrogen molecule ion. See, ion is always formed by the loss of the electron. So we see here that 1s orbital of hydrogen, this is 1s orbital of other hydrogen, but here there is no electron because that has been lost. So we'll just put in the molecular orbital 1 electron. So the bond order we will calculate will be 1 minus 0 over 2. So half is the bond order of this hydrogen molecule ion, and this is the electronic configuration, that is sigma 1s1, right? So this shows that the bond order is half. First, this is the electronic configuration, this is the bond order, also this is paramagnetic, right? This hydrogen molecule is diamagnetic because of the presence of these two electrons, and this hydrogen molecule ion is paramagnetic because of the presence of one electron. Now we come to the formation of the helium molecule. See, the helium molecule is having atomic number 2. The electronic configuration is 1s2, right? So in this 1s2 configuration, we'll put it like this. This is one helium, this is another helium. The two join to form the helium molecule. So as there are two atomic orbitals, so two molecular orbitals will be formed. And as a result of this, let's do the filling now. There are 4 electrons are to be filled. So 2 will be filled here, 2 will be filled here. Let's now calculate the bond order. The bond order will be what? Half sum of bonding electrons minus anti-bonding electrons. So that comes out to be 0. So that means the helium-2 molecule does not exist. Now important question that can come from here is that justify that helium molecule does not exist on the basis of your molecular orbital theory. See, you can justify this, that helium molecule does not exist on the basis of valence bond theory. So any question can come in the paper, and then you have to use accordingly the theory. So that means helium-2 molecule does not exist, right? Because helium being a noble gas does not form bonds with others. Now we come to the helium molecule ion. See, again I have told you when that ion is formed by the loss of the electron. So here we see that from one electron will be lost from here. So electrons are generally lost or gained in the anti-bonding molecular orbital. This is the bonding molecular orbital. This is anti-bonding molecular orbital. So one electron will be lost from here. Now you can see here the bond order. So the bond order will be what? 2 minus 1 over 2. Right? So the bond order for helium molecule ion will be half. So as there is one electron in case of helium molecule ion, so we'll call this as a paramagnetic species, right? Now we come to the lithium molecule. See, lithium has atomic number 3. Its electronic configuration is 1s2, 2s1. So here we will not consider the inner orbitals because they do not take part. They do not participate in the bond formation. So we'll simply write about the 2s orbital. Let me show you how we can write for this. See, lithium atomic number 3, electronic configuration 1s2, 2s1. So I will ignore this because the inner orbitals do not participate. So I'll write like this. So as a result of this, now this is the molecular orbital formed by the joining of these atomic orbital. So sigma 2s, as there are 2 electrons, so we'll put this here. The bond order will be half sum of bonding minus anti-bonding orbitals. So half of 2 minus 0, that is 1. So that means in lithium there is a single covalent bond, and we can write like this. So the electronic configuration we can write as sigma 2s2, right? This shows the number of electrons in that orbital. This is the sigma orbital, so we'll write sigma 2s2. This indicates the inner shell which do not participate, that is 1s orbital. In some books it is mentioned about 1s, so but we generally ignore it. So we can write, instead of writing about the 1s, we can simply write the kk shell, that is the inner shell, right? Now we will discuss about the important molecule, that is the oxygen molecule. Let me first discuss about oxygen molecule. We know the atomic number of oxygen is 8, right? So the electronic configuration will be 1s2, 2s2, 2p4. Okay, so again I will ignore the 1s orbital. I'll simply write the 2s. So I'll start from 2s. This is 2s of one oxygen, this is the 2s of the other oxygen. So they join to form the molecular orbital, that is O2. So that one will be bonding, another will be anti-bonding. So I'll write here sigma 2s anti-bonding, right? Now I'll write about 2p. So 2p has 4. First I'll write 3 and then pairing will start. Hund's rule of maximum multiplicity. See, this for 2p and this is another 2p for the second oxygen atom. So here as we know that p orbital has px, py, pz. The pz, they are along the internuclear axis, so they form the sigma bond. So I'll write first sigma 2pz and this is sigma 2pz antibonding. Corresponding to every bonding there is an antibonding orbital. Now as the px and py form the pi molecular orbitals, so they have lesser energy, more energy than sigma 2pz but less energy than the sigma 2pz antibonding. So I'll write like this. So pi to px, pi to py, and then corresponding pi to px antibonding, pi to py antibonding. Now I have to fill these 8 electrons in these bonding molecular orbitals. So 2, 4, 6, 7, 8. Now let me calculate the bond order. The bond order will be, it will be 8 minus 4. Let me show you here. It is 2, 4, 6, 8. These are the bonding orbitals, and 2, 3, 4. These are the antibonding molecular orbitals. So 8 minus 4 over half, that is 2. That means the bond order is 2, which shows that oxygen is having a double bond, right? So oxygen has double bond. As there are unpaired electrons in these antibonding molecular orbitals, so this is a paramagnetic species. Fine. Okay, so this is the way we write the electronic configuration. This indicates the inner shell. Sigma 2s having 2 electrons, sigma 2s star having 2 electron, then pi, this is sigma 2pz having 2 electrons, this is pi to px having 2 electron, pi to py having 2 electron, then pi star to px1 and pi star to py1. So they are having 1 electron each, right? So this is the way we have we can write the electronic configuration. So we have calculated the bond order and we have come to know that oxygen is a paramagnetic species. Now let's do this very important question, the comparison between these different species of oxygen. So let's talk about oxygen molecule ion. So this has been formed by the loss of 1 electron. Okay, now the gain or loss of electron will be in the antibonding molecular orbitals. So what I will do, in order to make this energy level diagram for this oxygen molecule ion, I'll just remove 1 electron from here. I'll show you. The rest everything is same, only 1 electron will not be there in one of the orbitals. So now we have the number of antibonding, let's calculate the number of bonding molecular orbitals, that is 2, 4, 6, 8. So 8 minus the number of antibonding molecular orbitals, 2 and 3. So number of electrons in the antibonding molecular orbitals. So this is 8 minus 3, that is 2.5. So this is the bond order of O2 positive, right? So electron will be added or gained, electron will be added or removed from the antibonding molecular orbital. This is what you have to keep in mind, right? Now we come to the next species, that is O2 negative. Now this O2 negative is formed when one electron will be gained here, right? So one of these orbital gains 1 electron. Say this has gained 1 electron. So I'll write that added electron here. Okay. Now, so what will be the bond order in case of O2 negative, which is called a superoxide ion. So the name is also important. So this superoxide ion have bond order 8 minus 5. Because 1 electron has increased here, So this is the bond order, that is 1.5 will be the bond order of superoxide ion. Then we talk about the bond order of peroxide species. Now in peroxide species you see 2 electrons are being added. So these 2 electrons will be added in this antibonding molecular orbital. So let's see the bond order here. So bond order will be 8 minus 6, right? So 8 is 2, 4, 6, 8 and 6 is 2, 3, 4, 5, 6. 2 have been added in case of O2, 2 negative. So the bond order comes out to be 1. Okay, so this is the bond order for the peroxide ion. And this is the electronic configuration. As the electrons are being filled, accordingly you will write this molecular orbital electronic configuration. Fine. So this is regarding the oxygen molecule. Let's now understand the molecular orbital energy level diagram of nitrogen. See, nitrogen has atomic number 7. Its electronic configuration is 1s2, 2s2, 2p3. We can split it and write, because every orbital, p is having 3 orbitals, px, py, pz, and every orbital will get 1 electron. Now let's see how to make the energy level diagram. See, we will not consider the 1s orbital as they are inner orbitals, so they do not participate in bond formation. And we start with 2s. So this is 2s of one nitrogen atom, this is 2s of the other nitrogen atom. These atomic orbitals, they overlap to form the molecular orbital, and we can write sigma 2s and sigma 2s antibonding. Now let's talk about 2p orbitals. So 2p has 3 electron each. This is having 3 electrons. Now one important difference between the energy level diagram of nitrogen and oxygen is that in comparison to the oxygen, see, in case of nitrogen, this level shifts here and this level shifts here. This is the only change that you find in the nitrogen, this molecular orbital energy level diagram. And this change is applicable to all the molecules below nitrogen, that is carbon, beryllium, lithium. So this is applicable. This change is the result of the fact that these two orbitals lie very close to each other, that they exchange their positions, right? So we will fill these electrons now. In case of this 2p, there are 3, this 2p3, so there are 6 electrons to be filled. So 2, 4 and 6. So let's calculate the bond order. The bond order is half sum of bonding electrons. So 2, 4, 6, 8 minus the anti-bonding, 8 minus 2 over 2. So that comes out to be 6 over 2, and that is bond order in case of nitrogen is 3. So we know that nitrogen has 3 bonds. So this is how you will write the electronic configuration. Kk means the closed, this is the inner shell. Okay, so we'll, instead of writing 1s bonding and 1s anti-bonding, we can write Kk here. So there are 3 bonds. As we see in nitrogen, there are 2 electrons in the higher uppermost energy level. So this is a diamagnetic molecule. So this species is diamagnetic. Now let us compare the nitrogen with N2 positive. When I say N2 positive, means 1 electron has been lost. The loss will be from this orbital. Okay, now let's calculate again the bond order. It is 2, 4, 6 minus this is 2, 4, 6, 7 minus 2. So the bond order will be 7 minus 2 over 2, that is 2.5, right? So the electrons, they are lost. Here the electron is lost from the bonding molecular orbital. Okay. So the bond order comes out to be 2.5, and in case of nitrogen, the bond order is 3. As there is 1 electron in case of N2 positive, so this is a paramagnetic species. So N2 positive is paramagnetic, right? So this is what you need to keep in mind.